So let's look at a couple of examples of how to apply partial fraction decomposition to integrals. Starting with the one on the left. So the procedure for part A is first of all to factor the denominator, recognizing that the integrand is 1 over x squared plus x minus 2. Factoring, we have 1 over x plus 2 times x minus 1. These are both linear factors, and so we would set this equal to a1 over x plus 2 plus b1, or rather a2, over x minus 1. Multiplying both sides by x plus 2 times x minus 1, we would have 1 equals a1 times x minus 1 plus a2 times x plus 2. Distributing, we have 1 equals a1x minus a1 plus a2x plus 2a2. Combining like terms, we're going to be setting, assuming there's an unwritten 0x term here. So what we see is that the a1 term plus the a2 term must be equal to 0, and that the negative a1 and the 2a2 must be equal to 1. This is actually the same fraction that we decomposed earlier. And so that means that 3a2 equals 1, which means a2 is 1/3. And we can conclude then that a1, being the opposite of a2, has to be negative 1/3. And so what this means is that the integral of dx over x squared plus x minus 2, or in other words, the integral of 1 over x squared plus x minus 2 dx, is the same thing as integrating the sum of a1 over x plus 2, which is negative 1/3 over x plus 2, plus a2 over x minus 1, 1/3 over x minus 1 dx. Now remember, the reason we're doing this is because we couldn't let u equal x squared plus x minus 2, and this isn't in a form that we can integrate, not easily anyway, and so we're using the option of partial fraction decomposition. However, in this case, we can let u be x plus 2, and separating these into two separate integrals, in this side we can let u be x minus 1. So let's consider bringing negative 1/3 out front and looking at 1 over x plus 2 dx, plus bringing positive 1/3 out front and looking at 1 over x minus 1 dx. And so on the left here, letting u equal x plus 2, du will equal dx. And so we're going to have negative 1/3, the integral of 1 over u du, which is the natural log of u. So we have negative 1/3 natural log of the absolute value of u. Putting in our u, we have negative 1/3 the natural log absolute value of x plus 2. Now over here, we're going to have 1/3 times the u is going to be x minus 1, du again is just dx. So it's 1/3 the integral of 1 over u du again, which is 1/3, and if it bothers you to have the same variable, you can always use a v or a w. So we'll have 1/3 natural log of u, which in this case is 1/3 natural log absolute value of x minus 1. These are being added, remember, and then we have our plus c. So that's how we can use partial fraction decomposition to integrate. Now in the next slide, we're going to look at part B. Alright, now let's look at part B here. Now, part B is a little different from the other fractions or rational expressions we've looked at because it's an improper rational expression in the sense that the numerator has a higher degree than the denominator. So before we start trying to use partial fractions, we're actually going to just do some long division and rewrite this expression. So let's get a pen going here. So in part B, we're going to take x squared plus 6x plus 10, and we're going to divide it into x to the fourth plus 6x cubed plus 10x squared plus x plus 0. Notice we have all of the powers of x represented except no x, so I'm going to put a little 0 there. Now dividing x squared into x to the fourth gives us x squared. Put it over the proper term. Distributing, we have x to the fourth plus 6x cubed plus 10x squared. Subtracting, we get a 0x squared and a 0x cubed. And we bring down an x. And x squared goes into x cubed once, so we have 1x. Distributing, we have, I take that back. It goes into 0x squared 0x times. So we're going to have 0x cubed plus 0x squared plus 0x. Subtracting, we have an x, bring down a 0. X squared does not go into x anytime, so that's going to be a 0 again, or you could think of it as using the last three terms. 0x squared is the leading coefficient, so you multiply by 0. You have 0x squared plus 0x plus 0. Subtracting, we have just an x. So what we found here is, and remember this x has yet to be divided by that. So our original expression, x to the fourth plus 6x cubed plus 10x squared plus x over x squared plus 6x plus 10 is actually equal to x squared plus x over x squared plus 6x plus 10. Now, in this case, we know how to integrate x squared, and also if we let u be the denominator, our du will be 2x, and we have an x, so we actually don't have to use partial fraction decomposition in this particular problem. So let's go ahead and set that up. So we have the integral of x squared plus x over x squared plus 6x plus 10 dx. We're going to separate that into two separate integrals, the integral of x squared dx plus the integral of x over x squared plus 6x plus 10 dx. Okay, in this case there's no substitution required. We know that we just get x cubed over 3 plus, over here we're going to need a 2 that we're missing, so we'll have to compensate by a 1/2 on the outside. And we're letting u equal the denominator. So we'll have 1/2 the integral of du is 2x dx. So we'll have du over u. Now this is going to give us x cubed over 3 plus 1/2 the natural log of the absolute value of u. And yes, a lot of times we do get natural logs. And this is going to equal x cubed over 3 plus 1/2 the natural log, the absolute value of x squared plus 6x plus 10 plus c. So again, if you have a rational expression, substitution is not immediately obvious. It's not going to work. Make sure that for the improper fraction situation that you use long division to rewrite it. It's possible that you might need partial fractions to integrate whatever remainder is out here, but you may not.